Okay, so on Wednesday morning, we started section 8.1. We were looking at using the basic integration formulas from your textbook. You might remember I showed you a big table. There were over 20 formulas that we've gone over at this point now, between Calculus 2 and your Calculus 1 class. And you should be familiar with all of those formulas. You might not have the newest ones, like the inverse hyperbolic functions you might not have memorized quite yet, but you should be familiar with them and how to use them, and in the process of getting those memorized by working through problems. So we took a look at those basic formulas last time, and then the idea in this chapter is that we want to use those basic formulas as a starting point to be able to do even more complicated, harder, more challenging kinds of problems. So the kinds of problems that we're going to learn how to do now involve things like using trig formulas, or maybe some algebraic techniques that you learned maybe back in high school, like completing the square, using conjugates, and polynomial long division, all sorts of things. And we're going to put these ideas together to do more and more challenging problems. So let's just work back through the kinds of things that we did last time. We had to complete the square on this problem underneath this square root in order to make it look more like the arcsine formula. So completing the square is something that you'll need to practice on the homework. See, we also did a problem where we had to remember an old trig formula that you might not have seen for a while, maybe not since your geometry class or your pre-calc class. So this was an angle sum formula that lets us recombine this kind of complicated expression back into a single cosine. This one that's much easier to integrate using one of our basic formulas. In the next problem, we had to use the idea of the conjugate. So that's changing the plus sign to a minus sign in between two terms, or a minus sign to a plus sign, as in this case. And this is something that you learned probably in your algebra class in high school as a method to get rid of square roots underneath fractions. So if you wanted to get rid of this square root 2 minus square root 3, you would multiply and divide by the conjugate. So you're multiplying by 1. And what this does is let you get rid of this square root in the denominator. And the same kind of thing can work in calculus. In this case, the 1 minus cosine x became a 1 minus cosine squared x, which we could use another trig formula on, this time the Pythagorean theorem, to simplify into a single sine squared. And then this was the last problem we got to on Wednesday morning, I believe. We looked at this integral where we have a polynomial divided by another polynomial, but the power on top of this fraction is larger than the biggest power on the bottom. And this is something like an improper fraction. And in order to fix an improper fraction with polynomials, we have to do polynomial long division. And that's what we did on this problem. So we divided 3x squared minus 7x by 3x plus 2. And our answer was x minus 3 with a remainder of 6. And that let us rewrite the problem into a form that we could actually find an integral for. Do you guys have any questions over this material that we covered last time? Okay, So if you do think of the question, please be sure to ask it. But since no one is saying anything, we'll just move along to the last two examples that we need to work through. So number 5 here, we're looking at another rational, a rational function that we're trying to integrate. So a polynomial divided by another polynomial. But this one is not an improper polynomial like the last one. You see the largest power of x on top is x to the first power, and the largest power of x in the denominator is x squared. So long division won't help us in this case. If we tried to divide, we would just get this as a remainder. We wouldn't be able to do anything. When we end up with an expression like this, the first thing that you should do is try to think, is there some sort of u substitution that I can do to simplify things? In this case, you would probably think to put u in the denominator. So u equals 1 plus x squared. And then if you're going to do a u substitution, you also have to think about finding the corresponding du and figuring out where it goes into your integral. In this case, we would take the derivative of 1 plus x squared to get 2x, and then we tag on dx. So if we compare this u substitution that we might want to try to the integral as it's given to us, we can see a 2x and a dx from the du, but there's a problem here with the extra minus 1. So what we should do probably is separate the problem into two separate terms by dividing through the numerator by the denominator. So rewrite this essentially as two integral problems. So 2x over 1 plus x squared minus 1 over 1 plus x squared. So this u substitution that we talked about will work for the first term. Let's write that out. So the 2x dx, that becomes our du. And then over u. But we still have to deal with the second term here when we split up into two integrals, the 1 over 1 plus x squared. Do we have a formula that might let us do this problem? Anyone? Okay, it doesn't seem like anyone's helping me out here. So if you're not sure, what you should do is go to your textbook, which I was pulling up while I was waiting for you guys to give me the answer. And here is the table that we looked at on Wednesday. It's the table with the basic integration formulas that we've learned. So look through the table and see if you can find something that'll help us with this integral, 1 over 1 plus x squared. This one we know is going to be a logarithm. What is this one?
Would it be number 19?
Say that again?
Number 19.
Number 19, yeah. So number 19, we have a dx over a squared plus x squared. In this case, we have a 1 plus x squared, so our a is going to be 1. And this gives us a tangent function. Good, a tangent inverse. So number 19 is the correct one. Let's go back to the paper. So the first one is going to give us a natural logarithm. And remember, we have to put an absolute value around u, which is 1 plus x squared. And then this one is going to give us a tangent inverse. So there's a 1 over a in the front of the formula, but remember our a is 1, so we don't have to worry about it. And then we'll get an x on the inside. Maybe put some parentheses around that to keep it neat. And then add a constant since we're doing an indefinite integral. Good. Are there any questions over this example? No? Okay. So number 5, this example was a technique that you've seen before in many calculus problems where it's easier to break up an integral into pieces. Now we're just using that technique that you learned way back in Calculus 1 on something that's a little bit more complicated involving the new functions that we've learned about in Chapter 7. Now let's do number 6. So we're going to integrate from minus pi to pi, x to the 4th times sine of x. Okay, so let's go back to the table. And see if there's anything here that might help us. Anyone see anything? Okay, hopefully no one sees anything because there isn't anything in the table that's going to help us. The issue here is that we're combining a polynomial, something that we would use the power rule for, with a trig function, sine, that uses a totally different rule. Powers of x are given by rule number 2, whereas sine is given by rule number 6. And just using the information in the table, there's no obvious way to combine them. We don't actually have an integral rule for this one, or an integral formula. But my claim is that we can still do it, and this is actually a really easy integral if you think about it the right way. Does anyone have any other ideas?
Can you split it into two separate integrals?
No, that would be really nice if we could. So we can split integrals over addition or subtraction, like we did up here. We had a minus sign, so we were able to split it. But when we're multiplying functions, like in this problem, we don't have any rules, or at least not yet, that lets us split it into two separate integrals. So no. That's actually something that we're going to talk about in the next section, 8.2, how to split up two things that are multiplied together. But we don't know that one yet.
And can you use the power rule there?
So if we could split it up, then yes, we could use the power rule on this part and then the rule for sign on this part. But since they're being multiplied together, we don't really have any way to do them separately. So what we need is something, let's see, kind of running out of room here. Let's just write it here. What we need is something like the product rule.
Yeah,
But,
I think that's what I was thinking when I said power rule.
oh, okay, yeah. So that is what we need. But remember the product rules for derivatives. And we don't have an equivalent rule for integrals. Not yet. Like I said, that's what we're going to talk about in the next section. But we don't actually need any of that on this problem. We can actually just write down the answer without doing any work. So to give you guys some more intuition, let me graph. And then maybe just zoom in a little bit, since we're talking about an integral from pi to pi, or minus pi to pi. Let's see. Just trying to give us a better perspective. Does anyone see? Anyone see anything about the graph that might be useful?
It's not one-to-one.
It's not one-to-one, that's right. If you drew a horizontal line across it, then it would cross the graph more than once. Right. But remember, one-to-one, that had to do with finding inverse functions. And right now we're trying to do an integral, so we don't really care so much about inverse functions at the moment. Are there any other properties of functions maybe that could help us? Anyone remember what even and odd functions are? No one wants to say they remember what an even or an odd function is. That's okay, I guess. I guess I'll remind you. And so that I can write down that definition, let me temporarily go back to my paper. So an even function is one that's symmetrical across the y-axis. What that means is if you plug in negative x into your function, it's the same thing as just plugging in x. And an odd function is sort of the opposite. If you put in minus x, instead of getting f of x, the minus sign pulls to the outside. So minus f of x. Does anyone remember something about integrals with odd and even functions? I'm asking you to think back to calculus 1, I guess. So first of all, going back to our graph, can we tell if this is an odd or an even function that we're looking at? Is it symmetrical about the is it symmetrical about the y-axis?
No.
No, it's not just a mirror image. So it's not even. Is it odd though? If I go across the y-axis, is it flipped down to the negative?
Yes.
Yes. So this one is an odd function, which you should be able to tell me just by looking at it, if you're in practice with these sorts of things, because x to the fourth, because it has an even power, is an even function. And sine, you should know, is an odd function. And when you multiply an even and an odd together, they give you an odd. So just like when you multiply an even number and an odd number together, you're going to get an odd number. When you multiply even and odd functions, you get an odd function. Okay. So what happens when I integrate an odd function like this with symmetrical limits? So from minus pi to pi. Can you see in the graph what's going to happen? So from minus pi up to 0, we have this negative area below the x-axis. And then from 0 to pi, we have this positive area. And this shape is exactly the same as this shape. It's just been sort of mirrored across the y-axis and then flipped to the negative side. So what's going to happen when we add these two areas together? What do you think?
They're going to be 0?
Right, we're going to get 0. So without doing any work, any calculus work, let's say, we should be able to answer this integral is going to be 0. So when you're doing your homework, if you see an integral like this from negative a to positive a, where a could be any number, in this case it's pi. When you see an integral like this, you should think to yourself, am I looking at an even function or am I looking at an odd function? Because if you're looking at an odd function, you don't have to do any work. The answer is always going to be 0 when you have symmetrical limits like this. So any questions over that?
No, it just kind of reminds us of what we're doing when we're doing integrals.
Right. Yeah, there's a lot to think about.
Right. Well, I was thinking in terms of solving an integral and forgetting all about the fact that the whole point of this is area under a curve.
Oh, right. Yeah, so sometimes it can feel like you're just pushing symbols around when you're doing calculus, but there's really some geometry going on behind the scenes, even if you're not thinking about it. So integrals correspond to areas under curves. That's right. Okay, and that actually brings us to the end of this section, 8.1. So we just looked at lots of different um, ways that topics from other math classes, like trigonometry and algebra, they can come back into calculus and help us. Does anyone have any questions?
Well, I just have a question. Did you personally find it helpful to pull up graphs often, even if you didn't have to solve a problem?
To graph like the function that you're integrating? Let's see. I would say that most of the time it doesn't help a whole lot. The exception would be something like this, where you have these symmetrical limits and you might want to think about whether it's an even or an odd function. And the other exceptions, maybe I can write this down. So when graphs are handy or useful. Oops. So if you're in the problem, if you're explicitly thinking about area or volume even, because if you just try to integrate this function, let me bring up that picture again. If you just integrated this function, you're not finding the actual area under the curve or between the curve and the x-axis, because these areas underneath the x-axis are negative, so they cancel out positive areas. And if you wanted the actual area, you would have to remember that this integral from minus pi up to 0 is going to give you a negative number, and you would have to flip that around. You would have to change that into positive. So anytime you're doing problems about area under a curve, definitely make a graph. Under a curve or between curves, anything like that. Another time, so volumes, remember when we were doing volumes of revolution? And pretty much any time you're doing an application problem. So these are the times when I would, for this class, when I would think that I really need to make a graph. Did that answer your question?
Yeah, I was just wondering. I'm just trying to figure out how I'm struggling with calculus like I've never struggled with a math class before. I'm just not used to learning math by memorization. I usually was engaged with it.
Right. Well, with calculus, there are those formulas that you really have to have memorized, or at least, well, even if you don't have them memorized, you at least need them somehow in your memory bank, so that if you see an integral, it jogs your memory. Like, oh, I need to go look at this table because there's something useful here.
Yeah, like, are we going to be allowed to use the formula sheet on the test? Because I can certainly usually recognize when there was one I could use. But.
Yes. Yeah. For the upcoming test, I don't remember the exact date on it. It's in a couple weeks probably. Yeah, you'll be able to use a formula sheet.
Okay, thank you. 'Cause, yeah, I'm not going to have them memorized, but I can usually recognize when I confirm
Right.
it.
Okay, good. Are there any other questions or maybe some homework questions if anyone has thought of one.